Welcome to the review of waves using the June 2013 Physics Regents as our launch point. So you should have a reference table. We have a cut and pasted version of the relevant sections that will drag along with us. You should have a protractor. We also have one. And you should have a June 2013 Regents, some paper to write on, and a calculator if need be. Okay, what we're going to do here is talk about all the concepts involved in each question. So while this question may have a direct answer, we'll look at the other answers and we'll use them to help guide all of our thinking on waves. You can use one Regents essentially to review all of waves. You don't have to go through 10 Regents. What you can do as we go through a question, perhaps you should pause, figure it out yourself, put the video back on, and then see how well your thinking aligns with the ideas that I'm presenting. Okay, let's go. Which statement describes characteristic common to all electromagnetic waves and mechanical waves? Two terms you need to know. Electromagnetic waves. What you should be thinking is light. These are all the types of light. In fact, they're all listed on PRT, that's Physics Reference Table, page 2. Scroll up a bit. Here they are. All of these, the electromagnetic spectrum, are types of light. Gamma rays, X-rays, ultraviolet. We only see this strip, visible light, but they're all types of light. And it's useful to think of them as all types of light because there are certain characteristics they all have in common. Number one, in a vacuum, as is written on the front of your reference table, they all travel at a speed equal to the speed of light in a vacuum. This also brings to bear that light can travel in empty space. Please note, by the way, that this V is important. If a question ever asks you, at what speed is light traveling? The given, as you'll come to hear me call them, will be V, not C. They're looking for V. Okay, a second issue, all electromagnetic waves, all types of light, are transverse. If you remember the definition of transverse, it was that the vibrations are perpendicular to the direction of wave energy or wave motion. The proof for this was polarization. And yes, you may be asked about that. Okay, let's jump over here. Mechanical waves. Mechanical waves, well, you got lots of choices. You have sound is a very common one we'll talk about. You can have an earthquake. You can have just jumping on the ground, anything. Any sort of mechanical vibration. What that means is you take a slinky and shake it. There's a mechanical vibration. Basically, the definition here is that it has to travel through a medium with mass, aka a matter medium. Now what's this word medium? The word medium is actually the thing that the wave travels through. Do electromagnetic waves travel through a medium? Yes, the medium is the electromagnetic field, an invisible ocean in the universe. We'll worry about that some other time. Okay, so mechanical waves require this mass medium. They do not travel in the vacuum of space, and they can be, depending on the type, transverse or longitudinal. Now longitudinal, our number one example of that was sound. And longitudinal means the vibration is parallel to the direction of wave motion. Alright, so that's a quick thought process just based on these two. Now let's see where this goes. Both types of waves travel at the same speed. Well, light is at this speed, 3 times 10 to the 8th. Or some adjustment of that. Mechanical waves can be the speed of sound, they can be earthquake, they can go, that's not going to be the one, they can travel plenty of different speeds. Both require a material medium. Well, they both require a medium, but not material. Material is for mechanical only. So that's not the right answer. Both propagate in a vacuum. Well, we just talked about that. The vacuum is for electromagnetic only. That's not it. Both transfer energy. In fact, general rule, waves transfer energy. They do not transfer mass. Very important idea. This is part of what makes waves quick and cheap. Okay, let's go on to the next one. An electromagnetic wave is produced by charged particles vibrating. So again, electromagnetic, we're talking about light. When charged particles, that could be an electron, vibrating, they are actually accelerating, slowing down, then speeding up, then slowing down, then speeding up as they move back and forth. So when charged particles accelerate, you actually produce light. So here's the rate. A rate of 3.9 times 10 to the 8th vibrations per second. Ooh, well, what is that vibrations per second? That actually brings us to something called our three-word definitions. You should know a few three-word definitions. The three-word definition for frequency is cycles per time. Cycles, of course, could be vibrations or oscillations. The three-word definition for period is time per cycle. For wavelength is distance per cycle. And for wave speed is distance per time. You also have an equation for wave speed in your reference table. You can look that up. This one is from page 6, not page 5, where we find most of our wave information. All right, so anyway, vibrations per second is already the same thing as cycles per second. They're giving you a frequency. So what they're telling you here is the frequency is 3.9 times 10 to the 8th. The unit we have for vibrations per second is also the hertz. Now, when they give you types of light or electromagnetic energy, you have to go to the chart and look them up. This is a PRT2 problem. So, let's grab our chart. Let's bring it with us. And what you will notice is, look up top here, 3.9 times 10 to the 8th hertz. You go to the frequency axis. You find 10 to the 8th. 10 to the 8th is about here. Now 3.9 times 10 to the 8th is slightly bigger than 10 to the 8th, so you move towards 10 to the 9th. You find yourself somewhere around this region. So you're looking at maybe radio waves, TV, FM. Do we have that as an option? Yes, we do. Radio waves. Here's your answer. Okay, let's head on down to the next one. So let me pause a minute, so make this visually a little nicer. We'll bring this to the front. Good. So we don't see writing all over it. Okay, so we're bringing our reference table with us. Might as well bring our protractor with us too. Let's come on down here to question 18. So question 18. The energy of a sound wave is most closely related to. All right, this is worth your while and it's something you have to memorize. So energy of a sound wave. The energy of sound is most closely related to its amplitude. This is something you have to put in your mind, but one way you can think about this is, well, what's some way you can feel the energy of sound? Well, you can increase the volume. And you have to realize that the amplitude of sound is its volume. Now, that's a word that we define together, so amplitude and volume go together. You want to increase energy, you increase volume or amplitude, same thing. In fact, next time you're in the car and the music's too low, tell them, turn up the amplitude of that song, would you? Okay, so that you have to memorize, and of course there's your answer. But at the same time, you can know that the energy of light is actually not directly related to its amplitude. It's a little bit of a peek ahead to modern physics, but we have an equation. Where's it up here? Oh, we left some of this up here. We have an equation that tells us that the energy of light is related to its, don't have it right here, so let me just pull it up. Energy of light is related to its, one more, here it is, this equation. Photon is another word for light that we'll deal with later on. It's actually related to the frequency. So that's a useful thing that you can lean on later on. Okay, let's keep going. Pause for 1 minute while I link all these things together so they drag together. Pardon me. Okay, now let's go on to the next question. There we go. Now it's next question was 19. A sound wave traveling eastward. And so some of the information we learned earlier is going to start to lay over and help us out. So a sound wave traveling eastward. We have sound. We know a number of things about sound. So sound, first off, we mentioned above, we know that it is longitudinal. And through air, well, often they'll say through air at STP. They didn't say it here because it doesn't actually matter for this problem. But if you ever see at STP, they're talking about its speed, which is listed on the front of your reference table, 3.31 times 10 to the second meters per second, which, by the way, is just easier to write. It's 331 meters per second. Okay, so let's come back over here. So if it's longitudinal, remember that the vibrations are parallel to, so this is parallel vibration, parallel to the motion. So if the motion is east, let's call this north, call this then is east. Let's say the wave is traveling eastward, then the vibrations must be parallel to that, which means the vibrations will actually be back and forth, east-west. So there's your answer. A transverse wave would allow north-south. Okay, let's go on to the next one. What is the speed of light in ethyl alcohol? Excellent. Okay, so they will use this frequency equal 5.09 times 10 to the 14th hertz. The quick way to think about it is just like you do neglect friction when you're doing free fall problems. It's essentially telling you you are allowed to use the reference table. And the part of the reference table that you can use, of course, is this part, the absolute indices of refraction. It actually has that frequency listed. The reason it's there, of course, is these numbers change slightly when you change the frequency. But don't worry about that. That's not in this course. Okay, so we have a bunch of numbers here. And we have to figure out the speed of light in ethyl alcohol. Now, I mentioned this earlier. What is the speed of light? It doesn't say in a vacuum. So I'm going to do something called write your givens. Please write your givens. This is the key to getting any sort of quantitative question right. Write the list of what they've given you and also what you're looking for. So, the speed of light, this is not C, this is V. What is the speed? The frequency, now feel free to write it down, maybe it'll come in handy. As it turns out, this problem won't matter. Write it with your units. Ethyl alcohol, well that sounds strangely or oddly particular. If it is oddly particular, you probably have to look it up in the reference table. So let's scroll up a bit. Do we see anything about ethyl alcohol? Yes, we do. 1.36. So what is it, though, that's 1.36? You know, that's nice and all, but this is called an indice of refraction. And if you look, here we go. Your index of refraction is the letter N. So let's scroll down here. So N equals 1.36. So do we have enough to actually solve this problem? Well, this is everything they've given us, including what we're looking for. And that might be enough. So the next thing you do is you go and find an equation that might actually suit this list of givens. So we run up top, we have V, F, N. Not all of them are necessary. And we see, actually, here's an equation, N equals C over V. Well, we know C. C is the speed of light in a vacuum. That doesn't change. So we actually could use that equation. N equals C over V. If this were a part 2 question where you have to show your work, anything that shows up here should have units. So you can come back over and say, oh, well, the speed of light is 3 times 10 to the 8 meters per second. That's the speed of light in a vacuum. And then, of course, you just plug in your numbers. So I'll leave the math to you. I don't think you should have too much issue with it. Of course, you can look up answers to these, or if you have my packets, I give you the answers to them. So this one is a quick division problem. And by the way, this is a good time to pause and solve. Your answer should come out to this one. Okay. By the way, speed limit of the universe, all speeds have to be less than or equal to this 3 times 10 to the 8. So there are no choices here, but if you ever get a choice where the speed is greater than that, you made a mistake. Don't use it. Switch your math. All right, question 22. Here we go. We have a periodic wave. Actually, periodic is a term you need to know. Pardon me, I'm going to do one more grouping. Oh, seems to be ungrouping. Okay, let's pull them along with us then. So a periodic wave. Periodic, you do have to know the word. Periodic means it's repeating, and it also means that it's symmetric. Here's an example of a repeating wave that is not periodic, because it is not symmetric. So here's your axis. This is not a periodic wave. You notice the spacing is increasing. So that is not a symmetric, not a periodic wave. Anyway, let's come back over here. Which 2 points are out of phase? Let's talk about phase. Phase is basically a matching game. So, in phase equals the positions match, and I'll show you what I mean by that. In phase we'll do in red. A is in phase. In phase you can also say one cycle or one wave away from, so you're going to move a full wave from C. So A and C are in phase. B is in phase with D. Now the letters are not marked up here, but this spot, the crest, is in phase with the next crest. The trough is in phase with the next trough. Of course, this trough is in phase with the one before it. And the phasing can skip a wave. So you can be, there's in phase, and there's another in phase. So these 2 points are in phase. Great. Now a full wave, probably learned in math class, a full wave is described over 360 degrees. And this is useful, so you know in phase basically means the points are 360 degrees apart. They could also be 720 apart, that would be fine too. So when they talk about out of phase, there are actually possibilities. Out of phase is anything other than the 360. But common forms of out of phase are 90 degrees out, 180 degrees out, even 270 out, although these two are probably the most common. And so let's look at that. If A and C are in phase, which means they're 360 degrees apart, let's use green for 180 degrees out of phase. 180 is half of 360. So point A is 180 out of phase with, that's out a little too big, point A is 180 out of phase with point B. It's half a wave apart. The crest up here is 180 degrees out of phase with the trough down here. That's half a wave. Let's use point D. Point D is 180 degrees out of phase with half a wave away point E. Also with point C. Okay? Let's use 90 degrees out of phase. We'll do in blue. 90 degrees out of phase, 90 is a quarter of this, so you'd be only a quarter wave apart. So point A is 90 out of phase with the crest. Point B is 90 out of phase with the trough. And so hopefully you got the rhythm here. This question is much simpler, just out of phase. So it doesn't even matter. Now, as it turns out, all of these are right on the equilibrium line, which means you're only going to get 180 degrees out of phase. A and C, 360, that's in phase. B, hardly see them, and F, that's one wave, that's a second wave. 2 full waves, that's in phase. C and E, that's in phase. D, that's one wave, and then another half. So D and G are actually 180 degrees out of phase. There's your answer. All right, next one. A distance of 1 times 10 to the negative 2 meters, separates successive crests of a periodic wave in a tank of water. If a crest passes a point in the tank every 4 times 10 to the negative first seconds, what is the speed of this wave? Now, this is a question that by itself seems like there's a lot going on with the words. However, if you stick to your 3-word definitions and you set up your givens, you'll knock this out. So, let's go. A distance of that's a centimeter, separates successive waves. Now you could come over here and you could start writing distance and successive waves, but hopefully you recognize this is a waves problem. And so there's a couple of ways to approach it. One way to approach it is say, oh, wait a minute, successive crests, well, if you draw that, here's a crest, here's the next crest. Successive crests are crests that are next to each other. That actually is a cycle. So, we learned our definition before. Wavelength is defined as distance per cycle. So here, the wavelength is, here's the distance, 1 times 10 to the negative 2 meters, per successive crest, that's cycle. So we actually found our wavelength is 1 times 10 to the negative 2 meters. Okay, next one. A crest passes the point every 4 times 10 to the negative first second. Well, you can get a new crest, that's actually a new wave. That's also a cycle. So this given is actually 2 givens for us over here. If they give you a time and the number of waves, you can figure out both frequency and period. Now, is this overkill for this problem? Probably. But if you're able to do this, you'll get any problem of this sort. So, if they have time and waves, it's your job now for the 3-word definition. Frequency was cycles per time, and period was time per cycle. So let's just plug them in. Cycles, it's 1 over time, 4 times 10 to the negative first seconds. And period's the opposite, 4 times 10 to the negative first seconds over 1. You work this out. This is 1 divided by 0.4. That comes out to 2.5 hertz. And this, of course, comes out to just what it was, 0.40 seconds, 4 times 10 to the minus first. So we have all these nice givens, and finally what they're asking for is the speed. So we got lots of options here. The simplest option is to use that equation from your reference table. V equals F times lambda. You know F, you know lambda. You multiply these two, and you get 2.5 times 10 to the minus 2. Now I'll tell you, some of you may quickly look at this and say, oh, well that's a distance, and that's a time. And so if I just divide the two, I should get the right answer. And in this case, you will. But beware, you can look at this. V equals D over T. Beware that really what they're giving you is a wavelength and a frequency. But this too could work for this problem. Okay, come on to the next one. One vibrating 256 hertz tuning fork transfers energy to another 256 hertz tuning fork. Okay, there's some hints here that you should already know what's going on. If you see something that has to do with matching frequency, or sometimes you see the phrase natural frequency, and then you see the phrases transfers energy in the same statement, you're going to start to think resonance. This is when one vibrating object inspires another vibrating object to vibrate. So something hits something, something shakes something, rubs something, whatever it is. This 256 is shaking at the natural frequency, 256 of another, it'll start to shake as well. So the second tuning fork is vibrating. There you go, there's your resonance. Just as a reminder what these others are, diffraction is when waves spread around or behind a barrier. Reflection is when a wave bounces off a boundary. And refraction is when a wave enters a new medium. And there's a lot more richness to each of these, but we'll get into that in a little bit. Okay, so of course there's your resonance. 26. Sound waves are produced by the horn of a truck that's approaching. So we have waves, it happens to be sound, they are approaching a stationary observer. Okay, so compared to the waves detected by the driver, the waves detected by the observer. So this should give you an idea of, wait a minute, when there's either sound or light and two objects are either approaching or receding or sitting still, there's some sort of adjustment in the frequency here. This is a Doppler problem, a Doppler effect problem. So a little sketch may help you. If you have the truck driver and there's a horn, so there's a sound being made right here at the truck. And the driver can hear it. There's a person standing over here, and they also can hear it. The question is, what are they noticing and what is the truck driver noticing? The truck is driving off in this direction. So let me give you a few little breakdown samples over here. Breakdown is as follows. If the truck is sitting still, this is now the aerial view, or the top view. If the truck is sitting still, here's the driver. What you'll get are waves that move out around it in nice concentric rings like this. The truck is at rest. If the truck is moving to the right, this whole picture actually gets squeezed in this direction. So it's as if the source is chasing the waves. So we'll put our source here now, and the waves instead will take on a bit of a deformed shape, a bit more like this, where the waves appear compressed in front of the truck and stretched behind the truck. And so this picture alone tells you which way the truck is moving. This picture alone tells you the truck is heading off to the right. Of course, another picture, I should try to draw this one a little better. More obvious. There we go. This truck, of course, would be toward the direction of the compressed waves to the left. Anyway, these pictures alone tell you what's going on. An observer, let's look at this picture. An observer standing here at point A versus an observer standing here at point B will observe two different things. Now, at the truck driver notices no change. The driver himself, everything seems normal. You push the horn, whether you're driving fast, slow, or in between, it all sounds normal. But the observer, it seems a bit different. If the observer is standing ahead of the truck, where the truck is coming, the waves appear compressed. That actually is a situation where you have a small wavelength and therefore a big frequency. If you're standing away in the direction where the truck is moving away from you, you will notice a big wavelength and a small frequency. Of course, this is all premised on the fact that the speed of a wave depends on the medium. A lot of stuff to talk about here. So the speed of a wave depends on the medium. The medium here is air, if it's the sound of the horn traveling through it. So the speed is exactly the same. The speed at A is the same as the speed at B. And so the speed equation, which is V equals F lambda, actually tells us why this happens. You can see the wavelength has shrunk. The wavelength is this distance from crest to crest, from crest to crest. The wavelength on this side is this distance. You can actually put a ruler on it, this distance, if they give you a scaled drawing. Okay, so if the wavelength is small, the only way to keep this constant is you have to have a big frequency to compensate. All right, so we notice the driver notices no change, and the individual listening is now ahead of the truck. The truck is coming toward him. So if you were to draw these waves again, we would actually notice that the waves will appear more compressed. This is actually the situation where the person is here. If they're more compressed, you get a small wavelength, you get a big frequency. So, compared to the sound waves detected by the driver, the sound waves detected by the observer. Just as a matter of language, the question is always about the last thing they mention. So detected by the observer will have, well no, the speed depends on the medium. So the medium is the same. That's not the right answer. A greater, well we noticed it's not a greater wavelength. You're actually going to have a smaller wavelength. Frequency, yes, you will have a greater frequency. And period, well period is actually the inverse of frequency. So if the frequency is bigger, the period is actually going to be smaller as well. Okay, and that equation is on your reference table, page 5. Okay, let's go over here. So a physics student takes her pulse and determines that her heart beats periodically 60 times in 60 seconds. The period of her heartbeat. Now this is the third time, well definitely the second, potentially the third time in one Regents that the three-word definition is going to come in handy for you. So, what they're telling you, your givens, what have they actually provided? If it beats 60 times, that's the number of cycles. In 60 seconds, that's time. So you can find both frequency and period immediately. Frequency is cycles over time, which is 60 over 60 seconds. And period is 60 seconds, excuse me, let me give you the definition again. Time over cycles, which is 60 seconds over 60 beats. So the frequency is 1 hertz, and the period is 1 second. They can have the same number, but they are not the same. 1 hertz and 1 second are two different things. So the question, what's the period of the heartbeat? Well, you just did it. That's done. 1 second. Notice here, they gave you the different units. Both ones are here, and the answer with the wrong unit is given to you first. So if you move too fast, if you're not thinking about this, before you even do the question, you really should write yourself the unknown given. Period equals question mark seconds. I know period comes in seconds. Let me think about that before I get crazy about solving the problem. All right, let's go to 48. And here, only 2 more in part 1. We'll pause the video and then we'll make a part 2 video. All right, the diagram below shows 2 waves traveling toward each other. Now, they say in a uniform medium. Speed depends on medium. So they didn't even need to say this. This is redundant. Because by now we should be knowing that speed depends on the medium. So, they gave it to you twice. That's good. When both waves are in the region between points A and B, they will undergo. Well, you don't even need to know the details of what's happening there. You need to know the definition. So when 2 waves, or more, are in the same region, this can actually happen. This is called interference. Particles can't do this. You can't take 2 particles and put them in the same place at the same time. Objects that act like particles, they each occupy a volume and they bump into each other. Waves can actually pass right through each other without a problem. So, that's interference. Now, the type of interference, the best thing you can do here is called superposition. You don't have to know the word, but basically that means draw them on top of each other. Draw on each other. So, we'll do this wave on the left in green, and we're going to bring it over here, and we'll do the wave on the right in blue. Now, I understand, obviously, you don't have paper that allows you to draw and move, so just try to redraw it here. You see, it starts, put your points, and then this one drops, rises, drops. So it actually follows the same shape. Drop, rise, drop. Okay, they are in phase, which means they match. Before we did points in phase, now we have waves in phase. They match. And when they match, they add. They actually make not a smaller wave, but a bigger wave. In reality, what you would see here is